In the 21st century, we stand at the edge of a new era in discovery. We peer billions of years into the past using telescopes that orbit Earth and float in the cold vacuum of space. We send robotic explorers across the solar system, land them on distant moons, and launch probes beyond the heliosphere into the interstellar void. We build machines capable of recreating the conditions of the early universe, smashing particles together at near-light speeds to glimpse the fundamental forces that shaped reality itself. And yet, for all our progress, the universe remains a vast and enigmatic expanse, filled with wonders we can barely comprehend, phenomena that defy logic, and truths so strange they seem to belong to science fiction rather than scientific fact. Episode 1. The birth of everything. For every human being who has ever lived, there was always a sky above and a ground below, an unshakable reality that time had always flowed forward, that space had always stretched infinitely in all directions, and that the stars had always burned quietly in the darkness. But for all of our assumptions about the nature of existence, modern science tells us something far more profound. The universe had a beginning. Not just a beginning in time, but a beginning of time itself. This is one of the most revolutionary ideas in all of human history. That everything we see, everything we are made of, and everything we can possibly imagine came into being at a specific moment, roughly 13.8 billion years ago. That moment, known as the Big Bang, was not simply an explosion within space, but rather the birth of space itself. It was not merely a burst of energy in an already existing void, but the creation of the very fabric of reality. To understand this, we must first confront what it means to say that the universe began. The idea may seem abstract, even paradoxical, but it is supported by overwhelming evidence from multiple lines of inquiry. Observations of distant galaxies moving away from us, measurements of the cosmic microwave background radiation left over from the early universe, and the abundance of light elements like hydrogen and helium that match predictions of how matter formed in those first few moments. But how did it all start? To answer that question, we must go back, not just billions of years, but to the very first fractions of a second after the Big Bang. We must peer into a realm where the laws of physics as we know them begin to break down, where gravity merges with quantum mechanics, and where the very concept of time becomes uncertain. Imagine a universe smaller than a proton, hotter than anything we can comprehend, and denser than the core of a black hole. In that infinitesimal moment, all of space was compressed into a singularity, a point of infinite density and temperature. From this state, the universe expanded violently, rapidly cooling as it grew. This expansion wasn't just movement through space, it was the stretching of space itself. In the first fraction of a second, less than a trillionth of a trillionth of a trillionth of a second, the universe underwent a phase of exponential growth called cosmic inflation. During this period, the universe expanded faster than the speed of light, growing from subatomic scales to something much larger than our current observable universe in an unimaginably short amount of time. This theory of inflation was proposed in the early 1980s by physicist Alan Guth and later refined by Andrei Linde and others. It solved several problems in cosmology, such as why the universe appears so uniform on large scales, why it is so flat geometrically, and why we don't observe magnetic monopoles that should have been created in large numbers in the early universe. But inflation also raises new questions. What caused it? Was it a one-time event or part of a larger multiverse process? Could inflation be eternal? Meaning that while our universe stopped inflating, other regions continued expanding forever, giving rise to countless other universes? These are still open questions in cosmology, but they hint at the possibility that our universe may not be unique, that it could be just one bubble in an endless sea of inflating universes, each with its own laws of physics, its own constants, and perhaps even its own forms of life. Returning to our story, let's continue tracing the timeline of the universe's birth. After inflation ended, the universe was filled with a hot, dense plasma of elementary particles. There were no atoms, no stars, no galaxies, only a seething soup of energy and matter. In this extreme environment, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. In the first microseconds after the Big Bang, quarks and gluons roamed freely in a state of matter known as quark-gluon plasma. As the universe cooled further, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. Then came the era of nucleosynthesis, when protons and neutrons fused together to form the first atomic nuclei. For about 20 minutes after the Big Bang, the universe acted like a giant nuclear reactor, producing mostly hydrogen and helium, along with trace amounts of lithium and beryllium. This primordial mix of elements would become the raw material for the first stars, which would ignite hundreds of millions of years later, creating heavier elements through fusion and supernova explosions. But before any of that happened, the universe entered what scientists call the Dark Ages, a period lasting hundreds of millions of years, when there were no stars, no light, and no structure. Only neutral hydrogen gas filled the cosmos, absorbing any photons that might have traveled freely. It wasn't until the first stars formed, massive, short-lived giants, that the universe began to shine again. These stars emitted intense ultraviolet radiation, ionizing the surrounding gas and marking the end of the Dark Ages. This period, known as reionization, lasted for hundreds of millions of years and transformed the universe from a dark, neutral expanse into a glowing web of galaxies. Throughout all of this, another crucial piece of evidence emerged: the cosmic microwave background, CMB, a faint glow of radiation that fills the entire universe. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, the CMB is the afterglow of the Big Bang, light released when the universe was just 380,000 years old. At that time, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before this, the universe was opaque. Photons couldn't travel far without colliding with free electrons. But once atoms formed, light could finally move freely across space. That ancient light, now stretched to microwave wavelengths due to the expansion of the universe, provides us with a snapshot of the early universe, a map of tiny temperature fluctuations that correspond to the seeds of galaxies. These fluctuations, studied in exquisite detail by satellites like COBE, WMAP, and Planck, confirm the predictions of inflation and give us insight into the composition and evolution of the cosmos. So what does all of this mean for us? It means that we are not just observers of the universe. We are made from its ashes. Every atom in your body, except for hydrogen, was forged in the heart of a dying star. You are quite literally stardust, a product of cosmic recycling, born from generations of stellar explosions and galactic winds. Our journey from the Big Bang to today is not just a scientific story, it is a deeply personal one. It connects us to the cosmos in ways that transcend equations and data. It reminds us that we are part of something vast, something ancient, and something beautiful. And yet, even with all we've learned, many mysteries remain. Did time really have a beginning? What triggered the Big Bang? Could there be other universes beyond our own? And will the universe have an end? These are the questions that drive modern cosmology, the search for answers that may lie beyond the reach of our current understanding, waiting to be discovered by the next generation of explorers, thinkers, and dreamers. So as we continue our journey through the cosmos, remember this: we are not just studying the universe, we are part of its unfolding story, and the greatest chapters are yet to come. To understand the true origin of the universe, we must venture beyond the realm of classical physics and into the strange and counterintuitive world of quantum mechanics. In this domain, where particles can exist in multiple states at once, where cause and effect blur into probabilities, the rules of reality become fluid. And it is here, at the intersection of gravity and quantum theory, that some of the most profound ideas about the birth of the universe emerge. One of the greatest mysteries of modern cosmology is what exactly existed before the Big Bang, if such a concept even makes sense. According to Einstein's theory of general relativity, time itself began with the Big Bang. There was no before because time did not yet exist. But this raises a paradox. How can something begin from nothing? How does an entire universe emerge from a point of infinite density, a singularity, where all known laws of physics break down? Some physicists argue that the singularity is not a real physical object, but rather a sign that our current theories are incomplete. The equations of general relativity predict singularities inside black holes and at the beginning of the universe, but they do not account for quantum effects. To truly understand the origin of the universe, we need a theory of quantum gravity, a unified framework that merges general relativity with quantum mechanics. This is one of the holy grails of theoretical physics. Several approaches have been proposed over the years. String theory suggests that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings existing in 10 or 11 dimensions. Loop quantum gravity proposes that space itself is made up of discrete loops, a kind of quantum fabric that cannot be compressed beyond a minimum size. Other models suggest that our universe may have emerged from the collapse of a previous universe in a process known as the Big Bounce. But perhaps the most radical idea comes from physicist Alexander Vilenkin and others, who propose that the universe could have originated from nothing at all, through a purely quantum process. According to this hypothesis, the universe may have begun as a quantum fluctuation, a temporary disturbance in a vacuum that, under certain conditions, could give rise to a new universe. This might sound like science fiction, but it is grounded in well-established principles of quantum field theory, which tells us that virtual particles constantly pop in and out of existence in empty space. If such fluctuations can occur on subatomic scales, could a similar process have given birth to an entire cosmos? Vilenkin's model, known as the tunneling from nothing hypothesis, suggests that the universe could have spontaneously appeared in a state of zero size and then expanded into the vast cosmos we observe today. In this view, the universe didn't come from anywhere. It simply came into being because it could. This idea challenges our deepest intuitions about causality and existence. It suggests that the question, what caused the universe, may be fundamentally flawed because, in a quantum context, events don't always require a prior cause. They can happen probabilistically, without a deterministic trigger. Of course, this doesn't mean that the universe came from absolutely nothing. Some physicists argue that the quantum vacuum from which the universe may have emerged is not truly nothing, but rather a pre-existing state governed by mathematical laws. Others believe that the concept of nothing is inherently meaningless, that space, time, and even the laws of physics themselves may be emergent properties of a deeper reality we have yet to discover. Even Stephen Hawking explored this territory in his work on quantum cosmology. Together with James Hartle, he developed the no-boundary proposal, which suggests that the early universe had no distinct beginning in time, much like the surface of a sphere has no edge. In this model, time behaves like another spatial dimension near the origin of the universe, and the Big Bang is not a sharp moment of creation, but rather a smooth transition from a timeless state. These ideas remain highly speculative, but they represent the frontier of modern cosmology, where philosophy, mathematics, and physics converge in an attempt to answer the ultimate question: why is there something rather than nothing? Episode 2. Are we alone? For as long as humans have looked up at the night sky, we've wondered if we are truly alone in the universe. Is Earth unique? Or is life, perhaps even intelligent life, a common occurrence among the stars? In this episode, we explore one of the most profound questions in science and philosophy. Does life exist beyond Earth? We'll examine what conditions are necessary for life to arise, where in our solar system and beyond it might be hiding, and what efforts scientists are making to detect signals from civilizations far more advanced than our own. You'll also confront the famous Fermi paradox. If the universe is so vast and ancient, and if planets like Earth are so common, why haven't we found any evidence of other intelligent beings? This is a journey into the unknown, a search not just for life, but for meaning in the cosmos. The origins of life, from chemistry to complexity. How did life begin on Earth? That remains one of the greatest unsolved mysteries in biology. We know that simple organic molecules, the building blocks of life, can form naturally in space. They've been found in meteorites, interstellar clouds, and even in the tails of comets. Experiments like the Miller-Urey experiment, 1953, showed that amino acids, essential components of proteins, can form from simple gases like methane, ammonia, and water when exposed to lightning-like electrical discharges. But how did those molecules organize into self-replicating systems capable of evolving? One leading theory suggests that life began near hydrothermal vents deep in Earth's oceans, places where heat and minerals interact with seawater, creating complex chemical gradients that may have driven the formation of early cells. Another idea proposes that life originated in clay minerals, which can catalyze chemical reactions and provide templates for molecular replication. And some scientists believe that life didn't originate on Earth at all, that it was delivered here by asteroids or comets from elsewhere in the galaxy, a hypothesis known as panspermia. If true, then life may be spreading across the cosmos, carried on rocks ejected from planetary surfaces, seeding new worlds with the potential for biology. Where in the solar system could life exist? Despite its apparent uniqueness, Earth is not the only place in our solar system where life might exist or have existed in the past. Several worlds show promising signs of habitability. Mars, once warm and wet, Mars had rivers, lakes, and possibly even oceans billions of years ago. Today, it's cold and dry, but subsurface reservoirs of water may still exist, and with them, microbial life. NASA's Perseverance rover is currently searching for biosignatures in ancient Martian lake beds, while future missions plan to return samples to Earth for analysis. Europa. Jupiter's icy moon Europa hides an ocean beneath its frozen crust, a global sea kept liquid by tidal heating from Jupiter's gravity. Plumes of water vapor have been observed erupting from its surface, suggesting that Europa's ocean may contain the ingredients for life. NASA's upcoming Europa Clipper mission aims to study these plumes and assess the moon's habitability. Enceladus. Saturn's moon Enceladus has geysers that spray water and organic compounds into space. Analysis by the Cassini spacecraft revealed complex organic molecules and even hints of hydrothermal activity on the ocean floor. If life exists anywhere in our solar system besides Earth, Enceladus may be the most likely candidate. Titan. Titan, Saturn's largest moon, is covered in lakes and seas of liquid methane and ethane. Though too cold for water-based life, it may host exotic forms of life using alternative biochemistry, perhaps even methanogenic life that breathes hydrogen and eats acetylene. Its thick atmosphere and complex chemistry make it one of the most intriguing places in the solar system. Exoplanets and the hunt for habitable worlds beyond our solar system. Thousands of exoplanets, planets orbiting other stars, have been discovered. Many of them lie in the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. The Kepler Space Telescope and its successor, TESS, Transiting Exoplanet Survey Satellite, have identified dozens of potentially habitable worlds, including Proxima Centauri b, TRAPPIST-1e, and TOI 700d. Future missions like the James Webb Space Telescope, JWST, the Nancy Grace Roman Space Telescope, will analyze the atmospheres of these distant worlds, searching for biosignatures, gases like oxygen, methane, and ozone that may indicate biological activity. One day, we may find clear evidence of life beyond Earth, not through radio signals or alien visits, but through the faint spectroscopic fingerprints of photosynthesis on a world light years away. The search for extraterrestrial intelligence, SETI. While many scientists focus on detecting microbial life, others look for signs of intelligent civilizations. The search for extraterrestrial intelligence, SETI, listens for artificial radio signals from distant stars, hoping to catch a message from another civilization. So far, no confirmed signal has been detected, though there have been tantalizing candidates like the WOW signal, 1977, a strong narrowband radio signal whose origin remains unknown. More recently, SETI has expanded beyond radio waves. Scientists now search for optical signals, laser pulses, and even technosignatures, unusual patterns in starlight that might suggest megastructures like Dyson spheres baked around stars to harvest energy. Some researchers speculate that advanced civilizations may use quantum communication, neutrino beams, or even gravitational waves, technologies we don't yet understand. The Fermi paradox. Where is everybody? Given the age and size of the universe and the sheer number of potentially habitable planets, it seems statistically unlikely that Earth is the only place where life has evolved. Yet we see no evidence of extraterrestrial intelligence. No spacecraft, no signals, no artifacts, nothing. This contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Over the decades, scientists and thinkers have proposed dozens of possible explanations. We're rare. Intelligent life may be extremely rare due to the improbable combination of events needed for its emergence. They're listening too. Civilizations may be hesitant to broadcast their presence, fearing hostile encounters. The Great Filter. There may be a step in the evolution of life that is nearly impossible to pass, such as the development of intelligence or industrial technology. They're already here. Some suggest that aliens may already be observing us, choosing not to interfere, a concept known as the zoo hypothesis. They're post-biological. Advanced civilizations may have transcended biology entirely, existing as digital consciousness or artificial intelligence. They died out. Perhaps technological civilizations destroy themselves before they can expand into space through war, environmental collapse, or unintended consequences of AI. Each possibility raises unsettling questions about humanity's place in the cosmos and our own long-term survival. Philosophical reflections. The mirror of the cosmos. Finding life beyond Earth would change everything. It would confirm that biology is not a fluke, but a cosmic process, one that unfolds wherever the conditions are right. It would challenge religious beliefs, redefine our understanding of intelligence, and force us to reconsider what it means to be human. Even the mere act of searching, scanning the skies for messages, sending probes into the void, imagining what alien minds might be like, reflects something deeply human. Our need to connect, to understand, to belong. Whether we are alone or not, the search itself is a testament to our curiosity and courage, a reminder that we are explorers by nature, reaching out across the darkness, hoping to hear a voice calling back. Episode 3. The Life and Death of Stars. If the Big Bang was the birth of everything, then stars were its first great creations. Cosmic forges that transformed the raw elements of the early universe into the rich diversity of matter we see today. From their formation in vast clouds of gas to their explosive deaths as supernovae, stars are the engines of cosmic evolution. They shape galaxies, enrich space with heavier elements, and provide the energy needed for planets and life to exist. Without stars, there would be no light, no chemistry, no complexity. In many ways, they are the true architects of our universe. In this episode, we will explore the full life cycle of stars, how they are born, how they live, and how they die. We will journey from the cold depths of interstellar space to the violent heart of a dying sun. Along the way, we'll meet some of the most extreme objects in the cosmos: white dwarfs, neutron stars, and black holes, remnants of stellar death that continue to shape the universe long after their parent stars have vanished. The cradle of stars, nebulas and molecular clouds. Long before a star begins to shine, it exists as nothing more than a cold, dark cloud of gas and dust drifting through the galaxy. These clouds, known as molecular clouds or stellar nurseries, can stretch across dozens of light years and contain enough material to form thousands of stars. One of the most famous examples is the Orion Nebula, a glowing region visible to the naked eye under dark skies. Within it, dense pockets of gas collapse under gravity's pull, beginning the process of star formation. This process starts when external forces, such as shock waves from nearby supernova or gravitational disturbances from passing stars, compress parts of the cloud. As gravity takes hold, these regions begin to contract, heating up as they fall inward. Eventually, a dense core forms at the center, a protostar, surrounded by a rotating disk of gas and dust. This disk may later give rise to planets, moons, and asteroids, setting the stage for planetary systems like our own. The temperature and pressure at the protostar's core continue to rise until nuclear fusion ignites, marking the official birth of a new star. Nuclear fusion, the engine of light. At the heart of every star lies a furnace powered by nuclear fusion, the process by which lighter elements combine to form heavier ones, releasing enormous amounts of energy in the process. In stars like our Sun, hydrogen atoms fuse to form helium, producing light and heat that radiates outward. This delicate balance between the inward pull of gravity and the outward pressure of fusion defines a star's stable phase, known as the main sequence. But not all stars are alike. Their size determines their lifespan, brightness, and ultimate fate. Smaller stars, like red dwarfs, burn slowly and can last for trillions of years, while massive stars blaze brightly but die young, sometimes within just a few million years. Our Sun, an average yellow dwarf star, has been shining for about 4.5 billion years and is expected to continue doing so for another 5 billion before entering its final stages. The final stages, red giants and stellar evolution. As a star exhausts its supply of hydrogen in the core, fusion begins to shift outward into a shell surrounding the core. The outer layers expand dramatically, cooling and turning red, giving rise to what is known as a red giant. Inside the core, temperatures rise until helium begins to fuse into carbon and oxygen. In more massive stars, even heavier elements like neon, magnesium, and silicon can form in successive layers. Much like the layers of an onion, eventually fusion reaches iron, the endpoint of stellar nucleosynthesis. Unlike lighter elements, fusing iron does not release energy. Instead, it consumes it. When this happens, the star loses its internal energy source, and gravity wins. What happens next depends on the star's mass. The death of low-mass stars, white dwarfs, and planetary nebulas. For stars like our Sun, the end comes relatively gently. After shedding its outer layers in a spectacular display called a planetary nebula, the core remains behind as a dense, Earth-sized remnant known as a white dwarf. White dwarfs are incredibly dense. A teaspoon of their material would weigh several tons. They glow faintly from residual heat, gradually cooling over billions of years until they fade into darkness as black dwarfs. Though none have yet had time to form since the universe is still too young. Planetary nebulae, despite their misleading name, have nothing to do with planets. They are among the most beautiful objects in the sky, often displaying intricate shapes and vivid colors due to the interaction of stellar winds and ejected gas. The death of massive stars, supernova and neutron stars. Massive stars, those with more than 8 times the mass of the Sun, meet a far more dramatic fate. When fusion ceases in the core, gravity causes the star to collapse catastrophically, triggering one of the most powerful explosions in the universe, a supernova. These explosions outshine entire galaxies and release heavy elements into space. Elements like carbon, nitrogen, oxygen, gold, and platinum. These materials become part of the interstellar medium, seeding future generations of stars and planets. At the heart of the explosion, the core collapses further. If the remaining mass is between about 1.4 and 3 solar masses, the result is a neutron star, an object so dense that protons and electrons are crushed together into neutrons. Neutron stars are only about 20 kilometers across, yet they can spin hundreds of times per second, emitting beams of radiation like cosmic lighthouses, a phenomenon known as a pulsar. Some neutron stars merge with companions in binary systems, releasing gravitational waves detectable across the universe. Events that also produce heavy elements like gold and platinum in what are known as kilonovae, black holes. The ultimate fate of the most massive stars. When a star exceeds about 20 solar masses, even neutron degeneracy pressure cannot halt the collapse. The core continues to shrink, warping space-time around it until not even light can escape, forming a black hole. Black holes come in different sizes. Stellar mass black holes, formed from collapsing stars. Intermediate mass black holes, whose origins remain mysterious. And supermassive black holes, found at the centers of nearly all large galaxies. These supermassive giants, millions or even billions of times more massive than the Sun, play a crucial role in shaping galaxies. As matter falls into them, it heats up and releases enormous amounts of energy, sometimes outshining entire galaxies in what is known as an active galactic nucleus, AGN, or quasar. Black holes are not just endpoints of stellar evolution. They are active participants in the ongoing story of the universe. Cosmic recycling. How stars shape the universe. Every atom in your body heavier than hydrogen was forged in the core of a star or during its explosive death. This includes the calcium in your bones, the iron in your blood, the carbon in your DNA. All of it came from ancient stellar furnaces scattered across the cosmos. This process, known as stellar nucleosynthesis, is the reason the universe is filled with complex chemistry. Without it, there would be no planets, no water, no organic molecules, and no life. Stars are not just lights in the sky. They are cosmic recyclers, factories of creation, destroyers of worlds, and the very foundation upon which life is built. The legacy of dead stars, even after their deaths, stars continue to influence the universe. White dwarfs can explode as Type 1a supernovae if they accrete enough material from a companion star, providing astronomers with vital tools for measuring cosmic distances. Neutron stars can collide, producing ripples in space-time and creating some of the heaviest elements known. And black holes, despite being invisible, govern the structure of galaxies and may even regulate star formation itself. We are not separate from these processes. We are made of them. Every breath you take, every heartbeat, every thought you have is a continuation of the same cosmic cycle that began with the birth of the first stars. Episode 4: Galaxies and the Cosmic Web. If stars are the building blocks of galaxies, then galaxies themselves are the scaffolding upon which the entire structure of the universe is built. They come in all shapes and sizes: spirals like our Milky Way, massive ellipticals, and irregular dwarf galaxies scattered like debris across space. But galaxies do not exist in isolation. They are part of a grand cosmic architecture, an immense, web-like structure stretching across billions of light years. This structure, known as the cosmic web, is made up of vast filaments of dark matter and gas, connecting clusters of galaxies like threads in an enormous, invisible tapestry. In this episode, we will explore how galaxies form, evolve, and interact within this cosmic framework. We'll journey from the earliest proto-galaxies to the great superclusters that define the large-scale structure of the universe. Along the way, we'll uncover the role of dark matter, gravity, and supermassive black holes in shaping the cosmos. The seeds of structure, from quantum fluctuations to galaxies. The story of galaxies begins with the tiniest ripples in space-time. Quantum fluctuations imprinted in the early universe. These tiny variations in density, recorded in the cosmic microwave background, CMB, were the seeds from which all future cosmic structures would grow. As gravity pulled matter toward these denser regions, clouds of dark matter and gas began to collapse under their own weight. These collapsing clouds formed the first protogalactic halos, massive reservoirs of material destined to become full-fledged galaxies. Dark matter played a crucial role in this process. Unlike ordinary matter, it does not emit or absorb light, but it interacts gravitationally, making it the invisible glue that held galaxies together. Without dark matter, galaxies could not have formed so quickly or efficiently. Within these collapsing halos, gas clouds cooled and fragmented, giving birth to the first generation of stars, the population 3 stars, and marking the beginning of galaxy formation. The birth of spiral and elliptical galaxies. As time passed, these early star-forming regions merged and coalesced into larger systems. Some collapsed into rapidly rotating disks, forming spiral galaxies like our Milky Way. Others formed more spherical structures, evolving into elliptical galaxies, often the result of violent mergers between multiple smaller galaxies. Spiral galaxies are characterized by their flat, rotating disks and spiral arms, regions where new stars are actively forming. Their structure is maintained by angular momentum and the gravitational pull of both visible and dark matter. Elliptical galaxies, on the other hand, tend to be older, redder, and contain fewer young stars. They are often found at the centers of galaxy clusters, giant collections of hundreds or even thousands of galaxies bound together by gravity. Our own Milky Way is a barred spiral galaxy, about 100,000 light-years across, containing over 100 billion stars. It has been shaped by countless mergers throughout its history, including one with a dwarf galaxy called Gaia Enceladus around 10 billion years ago. And at its center lies a supermassive black hole, Sagittarius A star, with a mass of about 4 million times that of the Sun. Galactic mergers, the violent dance of galaxies. Galaxies are not static islands in space. They move, interact, and collide, sometimes merging to form entirely new structures. These collisions can take millions or even billions of years. Stars rarely crash into each other due to the vast distances between them, but gas clouds do, triggering bursts of new star formation. One of the most dramatic examples of this is the ongoing collision between the Antennae galaxies, two spiral galaxies currently locked in a cosmic embrace. Observations show streams of gas and dust being torn apart, while bright knots of newly formed stars illuminate the chaos. Closer to home, our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge, forming a new giant elliptical galaxy, often referred to as Milkomeda or Milkdromeda. This merger will dramatically reshape the night sky for any observers still present on Earth, though individual stars will likely remain unharmed. The role of supermassive black holes. At the heart of nearly every large galaxy lies a supermassive black hole, an object so massive that its gravitational influence extends far beyond its immediate surroundings. These black holes play a surprising role in galactic evolution. As matter falls into them, it heats up and releases enormous amounts of energy, sometimes outshining the entire galaxy in what is known as an active galactic nucleus, AGN, or quasar. This powerful radiation can regulate star formation by heating or expelling gas from the galaxy. In some cases, it may even halt star formation altogether, effectively determining whether a galaxy remains active or becomes dead. Quasars, the most luminous phase of AGNs, were common in the early universe. They represent a time when galaxies were still accumulating mass and their central black holes were growing rapidly. Today, many of these quasars have quieted down, leaving behind dormant supermassive black holes like the one in our Milky Way. Clusters, superclusters, and voids. Galaxies don't just form in isolation. They gather into groups, clusters, and superclusters, linked by vast filaments of dark matter and gas. The local group, for example, contains over 50 galaxies, including the Milky Way, Andromeda, and Triangulum. It spans about 10 million light-years and is part of the much larger Laniakea supercluster, which includes over 100,000 galaxies. Superclusters are among the largest known structures in the universe. However, they are not permanent. Over time, the expansion of the universe will stretch and separate them. Between these dense structures lie cosmic voids, vast regions with very few galaxies. These voids can span hundreds of millions of light-years and contain only sparse remnants of gas and dark matter. Together, these features, filaments, clusters, superclusters, and voids, form the cosmic web, a structure that reflects the underlying distribution of dark matter laid down in the early universe. Mapping the cosmic web. Thanks to modern telescopes and large-scale surveys, we now have detailed maps of the cosmic web. Projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have charted millions of galaxies, revealing the intricate patterns of the universe's large-scale structure. These observations confirm predictions made by cosmological models based on inflation, dark matter, and the expansion of the universe. One of the most striking discoveries came with the detection of the cold spot, a region in the cosmic microwave background that appears unusually cold and may be linked to a supervoid in the cosmic web. While its origin is still debated, it highlights how much we have yet to understand about the universe's structure. Future missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will provide even deeper insights, helping us map dark matter and study the growth of cosmic structures over time. The future of galaxies. Just as galaxies have evolved over billions of years, they will continue to change in the future. In the next few billion years, galaxy mergers will become less frequent as the universe expands and galaxies drift farther apart. Star formation will gradually decline as gas reserves are used up or expelled. Eventually, most galaxies will fade into dim, red collections of old stars, a fate known as cosmic senescence. Even the supermassive black holes at their centers will eventually run out of fuel. Though they will remain as silent sentinels, their influence will wane. And in the far distant future, trillions of years from now, the universe may enter a long, cold darkness, a state known as the heat death of the universe, where galaxies are isolated, stars have burned out, and even black holes have evaporated through Hawking radiation. But until then, galaxies will continue their slow dance across the cosmos, evolving, colliding, shaping the fabric of reality itself. Philosophical reflections, a universe of patterns. Looking at the cosmic web, this immense network of galaxies strung across the void like threads in a spider's web, one cannot help but feel a sense of awe. It reminds us that we are not just inhabitants of a single planet, orbiting a single star. We are part of a vast, interconnected system, a living, evolving universe, governed by forces we are only beginning to understand. Every galaxy, every star, every atom in your body is connected through the same fundamental laws of physics, laws that emerged from the earliest moments of the Big Bang and continue to shape the universe today. We are not separate from this cosmic structure. We are woven into it, part of a pattern that stretches across space and time. And as we continue to explore the mysteries of the universe, we begin to see ourselves reflected in the stars. Episode 5: Black Holes, the Invisible Titans. In the vast cosmic ocean of stars and galaxies, there exist objects so dense, so powerful, that not even light can escape their gravitational pull. These are black holes, the ultimate triumph of gravity over all other forces. Regions of space-time where the known laws of physics break down. For centuries, black holes were considered purely theoretical constructs, mathematical curiosities predicted by Einstein's equations, but too strange to be real. Yet today, we know they are not only real, but central players in the evolution of galaxies and the structure of the universe itself. In this episode, we will explore the nature of black holes, how they form, what happens at their edges, and why they may hold the key to understanding the deepest mysteries of reality. We'll journey from the event horizon into the heart of a singularity and ask whether black holes might be more than just cosmic voids, perhaps doorways to other universes, or even the foundation of a deeper truth about space and time. From theory to reality, the discovery of black holes. The story of black holes begins not with observation, but with mathematics. In 1915, Albert Einstein published his theory of general relativity, a revolutionary new way of thinking about gravity as the curvature of space-time itself. Only months later, German physicist Karl Schwarzschild found an exact solution to Einstein's equations, describing what we now call a non-rotating black hole. His calculations revealed something astonishing. If enough mass is compressed into a small enough space, gravity becomes so strong that nothing, Not even light can escape. This boundary became known as the event horizon, and the point at its center, where density becomes infinite, was called the singularity. At first, these ideas were seen as mathematical oddities rather than physical realities. Even Einstein himself doubted that such extreme objects could actually exist in nature. But over the decades, mounting evidence began to change minds. In the 1960s and 1970s, astronomers discovered powerful sources of X-rays in distant galaxies, emissions consistent with matter being heated to millions of degrees as it spiraled into invisible, massive objects. These were some of the first clues that black holes were not just theoretical, but real. Then came the detection of quasars, extremely bright, distant galactic cores powered by supermassive black holes devouring surrounding gas. Some of these objects outshone entire galaxies, emitting more energy than 1 trillion stars combined. By the late 20th century, black holes had moved from speculation to scientific certainty. Birth of a black hole. When stars collapse, black holes are born in the violent deaths of massive stars. When a star more than about 20 times the mass of the Sun exhausts its nuclear fuel, gravity wins. The core collapses under its own weight, triggering a supernova explosion that rips the outer layers of the star apart. If the remaining core is sufficiently massive, typically more than 3 solar masses, no known force can stop the collapse. Gravity crushes the core into a point of infinite density, a black hole. These stellar mass black holes are scattered throughout our galaxy, often detectable only when they interact with a companion star, pulling material into a swirling disk that emits intense X-rays. Some black holes grow larger through mergers. 2 black holes orbiting each other eventually spiral together, releasing gravitational waves, ripples in space-time, first detected by LIGO in 2015. These collisions provide direct evidence of black holes and open a new window into the universe, one that allows us to hear cosmic events previously hidden from view. Anatomy of a black hole, event horizon, accretion disk, and jets. Despite their reputation as cosmic vacuum cleaners, black holes do not actively suck in everything around them. Their gravity is no different from any other object of the same mass. Unless you cross the event horizon, the point of no return. Inside the event horizon, space and time become distorted beyond recognition. Time slows to a standstill for outside observers, while space curves inward toward the singularity, where density becomes infinite and the laws of physics cease to apply. Surrounding many black holes is an accretion disk, a swirling ring of gas and dust heated to extreme temperatures as it spirals inward. This disk glows brightly in X-rays and visible light, making black holes indirectly observable. Some black holes also produce relativistic jets, beams of high-energy particles ejected at nearly the speed of light. These jets can extend across thousands of light years, influencing the formation of stars and shaping the structure of entire galaxies. The information paradox: what happens inside a black hole? One of the greatest mysteries in modern physics is the black hole information paradox, a puzzle that has baffled scientists for decades. According to quantum mechanics, information cannot be destroyed. Every action leaves a trace. But if something falls into a black hole, including information encoded in particles, does that information vanish forever? Stephen Hawking proposed that black holes slowly evaporate over time through a process called Hawking radiation, a faint glow caused by quantum effects near the event horizon. If this radiation carries away energy, then over unimaginably long timescales, black holes should disappear entirely. But if a black hole evaporates completely, what happens to the information it once contained? Is it lost forever? violating the fundamental principles of quantum mechanics, or somehow preserved? This question remains unresolved, and it hints that black holes may be more than just cosmic voids. They may be gateways to a deeper understanding of reality itself. The holographic universe. Could we be living inside a black hole? Some physicists have gone even further, suggesting that black holes may contain entire universes within them, or that our universe itself may be a kind of hologram projected from the surface of a higher dimensional black hole. This idea, known as the holographic principle, proposes that all the information contained within a volume of space can be represented on its boundary, much like a 3D image encoded on a 2D surface. If true, this would mean that the universe is fundamentally two-dimensional, and that what we perceive as three-dimensional reality is merely a projection from the edge of a black hole's event horizon. While highly speculative, this concept has deep roots in string theory and quantum gravity, and it suggests that black holes may not be endpoints of destruction, but rather windows into a more profound layer of existence. Supermassive black holes, guardians of galaxies. At the heart of nearly every large galaxy lies a supermassive black hole, a monster, millions or even billions of times more massive than the Sun. Our own Milky Way hosts Sagittarius A star, a black hole 4 million times the mass of the Sun, and yet it is relatively quiet compared to others. Some galaxies harbor black holes that are actively feeding, creating brilliant quasars visible across the universe. These supermassive black holes play a crucial role in galaxy evolution. They regulate star formation by heating or expelling gas, and they influence the distribution of matter across vast distances. How did these giants form? One possibility is that they grew from smaller stellar mass black holes that merged over time. Another suggests that they formed directly from massive gas clouds collapsing under extreme conditions in the early universe. Whatever their origin, supermassive black holes are now understood to be central to the structure and dynamics of galaxies. Seeing the unseeable, imaging a black hole. For most of history, black holes were invisible, detectable only through their effects on nearby matter. But in April 2019, humanity achieved the impossible. We saw a black hole. Using the Event Horizon Telescope, EHT, a global network of radio telescopes linked together to form an Earth-sized observatory, scientists captured the first ever image of a black hole's shadow against the glowing backdrop of its accretion disk. The target was Messier 87, M87, a supermassive black hole at the center of the galaxy, Messier 87, located 55 million light-years away. The image confirmed predictions made by general relativity and provided direct visual proof of black holes' existence. A year later, the EHT team released a second image, this time of Sagittarius A+, revealing that even our own galaxy's black hole follows the same rules of physics. These breakthroughs mark the beginning of a new era in astrophysics, one where we can study black holes not just through indirect means, but directly observe their behavior and test the limits of our understanding. Black holes and the fate of the universe. Black holes may not just shape galaxies, they may also determine the ultimate fate of the universe. In the far future, trillions of years from now, stars will burn out. Galaxies will drift apart due to the expansion of the universe, and even planets will be torn away from their orbits. Eventually, the last remnants of matter will fall into black holes. Over unimaginably long timescales, even those black holes will evaporate via Hawking radiation, leaving behind a cold, empty universe filled only with low-energy photons and dark energy. But even in that darkness, black holes may leave behind echoes, imprints of information stored on their surfaces, or seeds of new universes waiting to begin. And perhaps, in ways we cannot yet imagine, black holes will remain the silent architects of reality, shaping not just galaxies, but the very fabric of existence. Philosophical reflections, the edge of understanding. Black holes challenge our deepest intuitions about space, time, and reality. They remind us that the universe is not bound by human logic. It is governed by laws we are still learning to interpret. They are both terrifying and beautiful, places where destruction and creation coexist, where time stands still, and where the unknown calls to us with a voice we are only beginning to hear. To look at a black hole is to peer into the abyss of knowledge, not with fear, but with wonder. It is to confront the limits of our understanding and to recognize that the greatest discoveries lie just beyond those limits. We are not separate from black holes. We live in a universe shaped by them, and in seeking to understand them, we come closer to understanding ourselves. Episode 7. Quantum reality and the nature of existence. At the heart of the universe lies a strange and counterintuitive realm, the world of quantum mechanics. It is a place where particles can be in multiple places at once, where observation changes outcomes, and where reality itself seems to depend on whether anyone is watching. This episode takes us into the deepest layers of existence, exploring how quantum theory has reshaped our understanding of matter, energy, and even consciousness itself. We'll examine the paradoxes that have baffled physicists for over a century, explore competing interpretations of quantum reality, and ask one of the most profound questions of all. Does the universe exist independently of an observer? Or is reality somehow shaped by perception? The birth of quantum theory. In the early 20th century, classical physics was shaken to its core. Scientists discovered that light, long thought to be a wave, also behaved like a particle, and that electrons, previously seen as tiny bits of matter, exhibited wave-like properties. Max Planck introduced the idea that energy comes in discrete packets, quanta, giving birth to quantum theory. Albert Einstein extended this idea with his explanation of the photoelectric effect, showing that light itself is made of particles called photons. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others built upon these discoveries, forming what became known as quantum mechanics, a new framework for understanding the behavior of atoms and subatomic particles. But unlike Newtonian physics, which described a deterministic, predictable world, quantum mechanics revealed a universe governed by probability and uncertainty. The double-slit experiment, a window into the quantum world. One of the most famous and perplexing experiments in physics is the double-slit experiment. Originally performed with light, it has since been conducted with electrons, atoms, and even large molecules. The setup is simple. Shoot particles toward a barrier with two narrow slits, then observe where they land on a screen behind. When unobserved, particles behave like waves, creating an interference pattern of bright and dark bands. But when you try to measure which slit each particle goes through, the interference disappears. The particles act like individual entities. Even more strangely, if you delay the measurement until after the particle has already passed through the slits, a setup known as the quantum eraser, the outcome still depends on whether or not information about the path is available. This suggests that the act of observation affects reality, a concept that has led to intense philosophical debate. Is reality only defined when we look? Do particles know they are being watched? Or does the universe only settle into a definite state when measured? The Copenhagen interpretation, reality through observation. The dominant interpretation of quantum mechanics is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg. It holds that quantum systems do not have definite properties until they are measured. Before measurement, a particle exists in a superposition, a combination of all possible states. Only when observed does the system collapse into a single outcome. This raises deep questions about the nature of reality. If nothing is real until it's observed, does that mean the universe only exists because someone or something is looking? Some have taken this to imply that consciousness plays a fundamental role in shaping reality, though most physicists caution against such conclusions without direct evidence. The many worlds interpretation. Every possibility becomes real. An alternative view was proposed in 1957 by Hugh Everett III, the many worlds interpretation, MWI. According to MWI, every time a quantum event occurs with multiple possible outcomes, the universe splits, each possibility becoming real in its own separate branch. In this model, there is no collapse of the wave function. Instead, all outcomes happen, just in different versions of reality. You, in this universe, made one decision today. In another, you made a different one. In yet another, you never existed at all. If true, the universe is constantly branching into an infinite number of parallel realities, each one just as real as this one. This idea may seem extravagant, but it has gained increasing support among physicists who see it as a way to avoid the paradoxes of wave function collapse. Quantum entanglement, spooky action at a distance. Another bizarre phenomenon predicted by quantum mechanics is entanglement, when two particles become linked so that the state of one instantly influences the other, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance, and for decades, physicists debated whether entanglement was just a mathematical curiosity or a real physical effect. Experiments have since confirmed that entanglement is real and that the correlations between entangled particles cannot be explained by any local hidden variables. This challenges our classical notions of space, time, and causality. It suggests that the universe may be fundamentally interconnected in ways we don't yet understand. Could entanglement be the key to understanding deeper levels of reality, perhaps even the structure of space-time itself? Quantum field theory, particles as excitations of fields. Beyond quantum mechanics lies quantum field theory, QFT, the foundation of modern particle physics. QFT describes particles not as tiny billiard balls, but as excitations of underlying fields that permeate all of space. For example, the electromagnetic field gives rise to photons. The electron field gives rise to electrons, and so on. These fields interact according to precise mathematical rules, forming the basis of the standard model of particle physics, one of the most successful scientific theories ever developed. Yet QFT still doesn't include gravity, one of the greatest unsolved problems in theoretical physics. Black holes and the information paradox. Quantum mechanics also plays a crucial role in understanding black holes, especially in relation to the black hole information paradox first posed by Stephen Hawking. Hawking showed that black holes slowly evaporate by emitting radiation, now known as Hawking radiation, due to quantum effects near the event horizon. But if a black hole eventually disappears, what happens to the information about everything that fell into it? According to quantum mechanics, information cannot be destroyed. Yet if it escapes with the Hawking radiation, how is it preserved? This paradox has led to some of the most radical ideas in modern physics, including the holographic principle, which suggests that all the information inside a volume of space can be encoded on its boundary. This hints that the universe might be a kind of cosmic hologram, a projection from a lower dimensional surface. Quantum biology. Is life fundamentally quantum? While quantum mechanics is typically associated with subatomic particles, recent research suggests that quantum effects may play a role in biological processes. For example, photosynthesis appears to use quantum coherence to transfer energy efficiently. Bird navigation may rely on quantum entanglement in proteins sensitive to Earth's magnetic field. Smell could involve quantum tunneling of electrons within odor receptors. These findings challenge the assumption that quantum phenomena are irrelevant at the scale of living organisms. They suggest that life may have evolved to exploit quantum effects, using them to enhance survival in ways we're only beginning to understand. Consciousness and the quantum mind. Some researchers have gone even further, proposing that quantum mechanics plays a role in human consciousness. Physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed the orchestrated objective reduction, OR theory, suggesting that microtubules inside neurons may support quantum processes that contribute to conscious experience. While controversial and lacking strong empirical support, this idea raises intriguing possibilities. Could consciousness be more than just neural activity? Could the mind be connected to deeper levels of reality through quantum effects? And if so, does that mean that consciousness is not merely an emergent property of the brain, but a fundamental aspect of the universe? These are speculative questions, but they highlight how deeply quantum mechanics challenges our understanding of both matter and mind. Philosophical reflections, a universe that observes itself. Quantum mechanics forces us to reconsider what we mean by reality. Is the universe an objective entity existing independently of observers? Or is reality a dynamic process, shaped by interactions, measurements, and perhaps even awareness? These are not just scientific questions, they are philosophical ones. And perhaps, in the end, science and philosophy will converge in our search for ultimate truth. Because if the universe is truly quantum at its core, then it is not a static stage where events unfold. It is a participatory process. We are not just observers of the cosmos. We are part of its unfolding story. Episode 8. The Future of Humanity in Space. For the first time in history, humanity stands at the threshold of becoming a multi-planetary species. We have walked on the moon, sent robotic explorers to Mars, and launched probes beyond the solar system into interstellar space. But our journey is only beginning. In this final episode of Mysteries of the Universe, a journey into deep space, we explore what lies ahead. From the colonization of the moon and Mars to the dream of interstellar travel, we examine how artificial intelligence, robotics, and genetic engineering will shape our future among the stars, and ask the ultimate question: what does it mean to be human in a universe that may one day belong to us? The return to the moon, stepping stone to the stars. After decades of absence, humans are preparing to return to the moon, not just for short visits, but to stay. NASA's Artemis program aims to establish a permanent lunar base by the 2030s. China and Russia have announced plans for their own International Lunar Research Station, while private companies like SpaceX and Blue Origin are developing commercial infrastructure for lunar exploration. Why the moon? It offers everything we need to begin building an off-world civilization. Water ice trapped in permanently shadowed craters can be extracted and split into oxygen and hydrogen, providing both life support and rocket fuel. Lunar regolith can be used as a construction material through techniques like 3D printing, allowing us to build habitats without launching everything from Earth. Its low gravity makes it ideal for testing technologies before sending them to more distant destinations like Mars. The moon is not just a destination. It is a launch pad for deeper space exploration. Mars, the red planet, our new home? Beyond the moon lies Mars, a cold, dusty world with a thin atmosphere and frozen water beneath its surface. It is the most promising candidate for human colonization in the solar system. Elon Musk's SpaceX has made it clear. Their long-term goal is to send humans to Mars and establish a self-sustaining city within the next few decades. NASA, ESA, and other space agencies are also investing heavily in Martian exploration. But colonizing Mars presents immense challenges. Temperatures average -60 degrees, -80 Fahrenheit. Radiation levels are dangerously high due to the lack of a global magnetic field. The atmosphere is too thin to support human life. Dust storms can last for weeks and cover the entire planet. Despite these obstacles, Mars remains our best bet for expansion beyond Earth. Using in situ resource utilization, ISRU, settlers could extract water, generate oxygen, grow food in pressurized greenhouses, and manufacture fuel for return trips or further exploration. Over time, terraforming, transforming the Martian environment to make it more Earth-like could become a possibility. This would involve releasing greenhouse gases to warm the planet, melting polar ice caps to release water vapor, and eventually creating a thicker atmosphere capable of supporting plant life. Whether in decades or centuries, Mars may become the second home of humanity, artificial intelligence, and the expansion of consciousness. As we move farther from Earth, human presence alone may not be enough. The vast distances, extreme conditions, and long travel times mean that artificial intelligence (AI) will play a crucial role in our future among the stars. Autonomous robots will prepare habitats, mine resources, and maintain systems before humans ever arrive. AI-driven spacecraft may even explore nearby star systems, traveling faster than any human crew could endure. Some scientists speculate that future spacefarers may not be biological at all, but digital minds, uploaded consciousnesses, living inside virtual realities aboard deep space vessels. This raises profound philosophical questions. What defines a person? Can consciousness exist independently of biology? If we upload our minds into machines, are we still human? These are no longer science fiction. They are real possibilities being explored by researchers today. Interstellar travel, reaching beyond our solar system, traveling to another star system, such as Proxima Centauri, the nearest star to our Sun, is currently beyond our technological capabilities. At current speeds, it would take tens of thousands of years to reach even the closest stars. But new propulsion concepts are being developed. Nuclear pulse propulsion, where small nuclear explosions push a spacecraft forward. Light sails, propelled by powerful lasers or sunlight. Antimatter engines, which could provide immense energy from tiny amounts of fuel. Warp drives, based on theoretical physics that suggest space-time itself could be manipulated to allow faster-than-light travel. While many of these ideas remain speculative, they represent the frontier of scientific imagination, and perhaps, one day, the key to reaching other worlds. Even if we cannot travel fast enough ourselves, we might send robotic probes to explore exoplanets and search for signs of life, or even seed life on barren worlds through directed panspermia. Human evolution in space, adapting to new worlds. As we settle on other planets, humans will inevitably change, not just culturally, but biologically. Microgravity, radiation, and alien environments will place evolutionary pressures on future generations. Over time, spaceborne humans may diverge from Earthbound ones, physically, mentally, and possibly even genetically. We may engineer ourselves using gene editing tools like CRISPR to adapt to low gravity, resist radiation, or live in pressurized domes. In extreme cases, we might even merge with machines, becoming cyborgs, part human, part machine. This transformation may not be optional, it may be necessary for survival. And as we evolve, so too may our sense of identity. Will future Martians see themselves as separate from Earthlings? Will lunar citizens develop their own languages, cultures, and governments? The seeds of interplanetary civilizations are already being planted, and with them, the potential for entirely new forms of human society. Why go to space? The ethical and existential imperative. Critics often ask, why invest in space when we have so many problems here on Earth? The answer is simple. We must look beyond ourselves. Space exploration is not just about technology. It is about perspective. It reminds us that we are part of something larger, that Earth is just one planet in a vast cosmic ocean. It fosters international cooperation, drives innovation, and inspires future generations. More importantly, it may be essential for our survival. Earth is vulnerable to asteroid impacts, climate change, pandemics, and even the eventual death of the sun. Becoming a multiplanetary species is not just a dream. It may be our best hope for long-term survival. The long view, humanity's cosmic destiny, looking far into the future, thousands, millions, even billions of years ahead. What becomes of humanity? Will we spread across the galaxy, building Dyson swarms around stars, constructing megastructures, and harnessing the power of black holes? Will we merge with artificial intelligence, transcending biology and evolving into post-human entities? Or will we fade away, a brief flicker in the cosmic timeline, remembered only by the echoes of our signals drifting through the void? Whatever the future holds, one thing is certain. We are no longer bound to Earth. We are explorers, pioneers, and dreamers. Beings who look up at the stars, not with fear, but with wonder. And as we continue our journey into deep space, we carry with us the hopes, dreams, and mysteries of every generation that came before. Philosophical reflections. A species among the stars. Humanity's story began under the open sky. Ancient eyes watching constellations shift, wondering what lay beyond. Now, we are poised to take our next great step, not just as individuals, not just as nations, but as a species. We are learning to live among the stars, to shape our destiny beyond the confines of a single planet, and to redefine what it means to be human. In the end, our greatest discovery may not be new worlds or new technologies, but a deeper understanding of ourselves. Because the universe is not just out there, it is within us. We are made of stardust. We are the universe observing itself. And our journey has only just begun.